Picture a standard Tuesday morning. Rush hour traffic, coffee in hand, heads down in phones. Then the routines stop. Every screen on the planet overrides with an emergency broadcast from an international coalition of space agencies. The announcement is brief, but the data is undeniable. Astronomers have verified the existence of a rocky, terrestrial planet resting perfectly inside its star's habitable zone. It has liquid water, a dense atmosphere, and a temperate climate. The coordinates point right next door. Look at this map of our local stellar neighborhood. The new planet is orbiting Proxima Centauri, the small red dwarf resting just below the Alpha Centauri binary system. The reaction ripples across the globe in distinct waves. Financial markets freeze, universities empty out. The initial profound awe quickly mixes with a creeping existential dread, as 8 billion people try to process that we are definitively not alone. For the first time in human history, our greatest existential loneliness is over. But having a confirmed destination creates a staggering new logistical nightmare. This new world is exactly 4 light-years away. In the vast scale of the universe, 4 light-years is effectively a shared bedroom wall in an apartment building. It is our absolute closest celestial neighbor. Yet human biology doesn't scale to cosmic maps. To reach out and touch that neighboring wall, we have to cross nearly 24 trillion miles of irradiated, freezing vacuum. We are looking through a clear glass window at a perfectly hospitable home, completely trapped on our side of a lethal environment. Before we commit the global economy to crossing 24 trillion miles, we have to be absolutely certain we aren't aiming at a barren rock. We need proof of life. We use transit spectroscopy. As the planet passes Proxima Centauri, starlight filters through its atmosphere. Elements block specific light wavelengths, creating a barcode of missing bands. These dark lines confirm the air's chemical composition, revealing water vapor and oxygen. Oxygen is highly reactive. Left alone, it binds with rocks and quickly disappears from an atmosphere. Finding a thick layer of it means something on the surface is actively replenishing it, a continuous biological process we call a biosignature. By reading the shadows hidden in starlight, we can verify an active, breathing biosphere without ever leaving Earth orbit. This timeline graph puts the travel distance into harsh perspective. An average human lifespan is roughly 80 years. If we launch our fastest chemical rocket today, it would take over 70,000 years to arrive. Chemical rockets burn liquid fuel to create thrust. To go faster, you need more fuel. But fuel is heavy, requiring you to burn even more fuel just to lift the extra weight. The physics creates a mathematical dead end. To cover interstellar distances, we have to move beyond controlled explosions and start engineering at the extreme edges of theoretical physics. Chemical rockets work for short hops to the moon or Mars, but they hit a hard wall when it comes to light years. Crossing that gap requires us to abandon the idea of burning fuel for thrust and look toward propulsion systems that don't carry their own weight. The immediate near-future solutions involve nuclear thermal rockets and fusion drives. Instead of burning heavy liquids, these engines use nuclear reactions to superheat a tiny amount of propellant, generating massive, sustained thrust over long periods. An even faster alternative ditches the onboard engine entirely. We could deploy massive, ultra-thin light sails in orbit and physically push them using arrays of gigawatt lasers built right here on Earth. The target metric for both technologies is velocity. We need a ship capable of maintaining between 10 and 20% the speed of light. At that speed, the math changes. A 70,000-year drift shrinks to a transit time of 20 to 40 years. It makes the journey achievable within a single human lifetime. Even before we assemble the first laser array or fusion reactor, the mere knowledge of an accessible second Earth alters our society. This discovery forces a global reevaluation of our place in the cosmos. For the first time, philosophers and theologians aren't debating theories, they're looking at a destination, challenging the long-held assumption that Earth is the only biological miracle in the dark. On a practical level, international priorities realign. Global supply chains, resource extraction, and engineering talent pivot toward constructing the immense infrastructure required for interstellar transit. Reaching Proxima Centauri stops being an academic goal and becomes a strategic one. We see a significant shift toward a massive orbital industrial complex as the promise of a second home begins to pull investment away from terrestrial projects and toward the stars. The timeline to design, test, and launch an interstellar mission will take decades. The central question is whether the sheer scale of the project unites competing nations or fractures our global economy under the immense resource strain. Solving the physics of light sails and fusion drives is only half the equation. Sustaining a unified, multi-generational effort requires a level of long-term cooperation humanity rarely demonstrates. The discovery of a second Earth, hovering 4 light-years away, acts as a mirror. It demands we answer a simple question. Before we try to inherit a second world, are we capable of managing the one we already have?